In this video, we're going to continue solving trig equations. This time, we're going to solve trig equations whose solutions and figure out a way to write the solutions that include all of the solutions, not just the ones within the first period. The process, though, is the same. It's only at the very end we're going to have to worry about writing our answer differently. We're still going to isolate the trig functions, undo them, and then solve whatever's left. Whenever we have a squared, well, let me say it this way. Whenever we have two different types of trig functions, either a sine and a cosine, or a cosine squared and a regular cosine, or any combination like that, we're really only going to be able to solve by factoring. So that's what I'm going to do here. I'll pull out the cosine of theta, which leaves me with 2 cosine theta plus 1 equals 0, and then we can split and solve. So this is very similar to the one we saw on the last screen. When we solve this, we can say, all right, when does the cosine of theta equal 0? For which angles are we talking about? You could write this as arc cosine of 0 if you want, but I think it's a little bit easier to kind of skip over that formality and just say, oh, the angles whose cosines are 0 are pi over 2 and 3 pi over 2. And on the other side, we have to get that cosine by itself, so I'll subtract 1 and divide by 2. And we say to ourselves, when does an angle have a cosine of -1/2? And remember, that would have to be in the second or third quadrants. The reference angle whose cosine is 1/2 is pi over 3. And so in the second and third quadrants, that would be 2 pi over 3 and 4 pi over 3. And so it looks like I've got 2 solutions. The problem is I've got more than 2 solutions to this equation. 2 times the cosine squared of x plus cosine of x. I want to know, when does this equal 0? Well, I can see that my solutions were right. Pi over 2, 2 pi over 3, 4 pi over 3, 3 pi over 2. That's great. I've got all 4 of those solutions. But the problem is it keeps happening. 5 pi over 2, 8 pi over 3. It keeps happening. And more. You can see there's all these zeros. So we need a way to write all of those zeros in one shot. And we're going to use the same strategy we used for domain of tangent and secant and all of that, when we just say, all right, if it's going to repeat itself every period, we're just going to write, this is going to be quite a long solution here, we're just going to write it as pi over 2 plus 2 pi n. There's no one correct way to order these. I like going in order from least to greatest. Some people like grouping the ones that came from the same place together. So some people might put 3 pi over 2 next. I like going in order from least to greatest. But you can say it however you want. And so this plus 2 pi n is our way of saying it's repeating itself every 2 pi radians. So we've got 4 infinitely repeating solutions, and that's how we write them. Okay, in our next example, same idea, everything's similar. The only thing is you might notice, oh no, there's 3 different trig ratios here, so am I going to have to split into 3 different groups and solve 3 different equations? Well, I can't really split that into 3 groups. There's nothing to factor there. So we need to use another strategy. And sometimes we need to simplify with trig identities first. So that is something to keep in mind in the back of your head, that the lesson we had last class sometimes comes into play in unexpected ways. Well, hopefully you see the tangent and quickly you see a good strategy to help here. Turn that tangent into sine of theta over cosine of theta. And then the cosines cancel out, and everything just got a whole lot easier. And we can go back to factoring the way we did before, pulling out the sine of theta. Remember, this doesn't disappear when we pull out the sine of theta. We're left with 1. And then we can split and solve. sine of theta equals 0 twice. It could happen at 0 or at pi. And 1 minus sine of theta, we'll add the sine of theta both sides. And sine of theta equals 1 only once at theta equals pi over 2. But there's a catch. Anytime you see tangent, cotangent, secant, or cosecant, or any denominator for that matter, little warning flags should go off in your heads that there is a domain restriction on all of those ratios. Anything except for plain old sine and cosine has a domain restriction. So you do need to check real quick. Theta cannot possibly equal pi over 2. Because right from the get-go, we had tangent of theta, which means that theta could never equal pi over 2. Or any other multiple of pi away from that. Because that is where the domain restrictions, the vertical asymptotes, are. So we're going to ignore that pi over 2 possibility. But theta still could equal 0 plus 2 pi n, or pi plus 2 pi n. And it's fine if you leave your answers like that. It's also fine if you take a look at that and say, wait a minute. If I were to make that list, 0, pi, and then repeating like every 2 pi. So 0 plus 2 pi, pi plus 2 pi. 0 plus another 2 pi, pi plus another 2 pi. You might notice this pattern. Oh, it's 0, pi, 2 pi, 3 pi. I could also write that as just pi n. And you're absolutely right. You can. If you write it like that, all power to you. I'm not going to be expecting it, so you don't have to look at your solution and say, wait, can I write that in a simpler way? But if you do, it's still correct. We'll look at a couple more examples here. For this one, hopefully you're not freaked out by seeing those coefficients there. We're still going to say the same thing. There's 2 different kinds of cosine there, one squared, one not, which means the only way we're going to get them both by themselves at the same time is by factoring. So we have to empty out that right-hand side, and we'll factor here. This looks a little bit different, but we have strategies for this. We know how to factor, and a good overall strategy I talked about in our logs unit is if you're ever a little bit confused by something looking weird, pretend it's not weird, and just factor. If you remember, the way we would do this is we would split up that negative 5x into 2 terms so we could factor by grouping. And the terms that'll work, we need numbers that will add up to negative 5x, but also multiply to negative 24. That would be negative 8x and 3x. So I'm going to do that split here. I'm going to take my negative 5 cosine theta, so I'm going to split it up, and you can split it up whichever way you want, it doesn't matter, into plus 3 cosine theta minus 8 cosine theta. We could have done these in either order that we wanted. That doesn't matter. It'll work both ways. And then we factor this by grouping. So I will pull out 3 cosine theta, which leaves me with 2 cosine theta plus 1. And I'll put out a negative 4, which leaves me with, hey, 2 cosine theta plus 1, just like we needed. So we can factor these out. 3 cosine theta minus 4 times 2 cosine theta plus 1 equals 0. The whole point of doing this was to get factors so we can use the zero product property, split and solve. And I'm going to do the one on the right first because it's simpler. Subtract 1 and divide by 2. And just like always, we say, all right, when does cosine of theta equal negative 1/2? Again, that's in the third and second quadrants. And we saw this one a second ago. The reference angles are pi over 3. So it's 2 pi over 3 and 4 pi over 3. On the right-hand side, things get a little bit weirder, but the solution, like the process isn't any different, even if the solution looks weird in the end. Cosine of theta, we're going to have to isolate that, so I'll add 4 and divide by 3. And we say to ourselves, when does cosine equal 4/3? And the answer is, of course, never. Cosine could never equal 4/3. There's no way a cosine is ever equal more than 1. This never happens. So if there's no solution from one of our factors, that's okay. We don't need there to be. Remember, the whole point of the zero product property is a product equals 0 if either factor equals 0. So theta could equal 2 pi over 3 or 4 pi over 3. And because the period here is 2 pi, we will write that as 2 pi over 3 plus 2 pi n, or 4 pi over 3 plus 2 pi n. And it's worth taking a quick look at the graph here. Hey, I didn't make it up. That is when 6 cosine squared theta minus 4 cosine theta minus 4 equals 0. One last problem to show you here. And notice, you'll very quickly notice the difference here, that there's a coefficient inside. We know what's going to happen when we do the solving. We saw this earlier in the last video, that it means that at the end, after we've figured out what angle the sine, has the sign of exactly the right number, we'll see in a second what that is, well, then we're going to have to divide by 2. Great. That we've already done. What's different in this problem is because we're going to be writing the repeated solutions using that plus 2 pi n, well, you have to remember that if the period changes, we need to change the period of our solution also. So that is something to think about when we see this. The period here is 2 pi over 2, which is pi. So when we're done here, we're not going to have our answer plus 2 pi n. It's going to be plus pi n. But once we've thought of that, everything else is the same as other problems. We will get it by itself. You can either factor here if you want, but because there's only one kind of sign, I would recommend you don't factor here. I would recommend instead you get the sine squared by itself, and then take the square root of both sides to turn it into regular sine. But what that means is we're going to end up with a whole bunch of possibilities, because now the sine of 2x could equal positive or negative 1/2. And we think, all right, what angle has a sine of positive or negative 1/2? Well, now it can be in any quadrant, because it can be positive or negative. And the reference angle whose sine is 1/2 is pi over 6. So that means 2x could be pi over 6. But it could also be pi over 6 in any of the other quadrants. So it could be that 2x is 5 pi over 6. Or 2x could be 7 pi over 6. That's in the third quadrant. Or 2x could be 11 pi over 6. That's in the fourth quadrant. So we've got 4 possibilities here. In all of them, we still haven't figured out what x is. But that's easy. We just divide everything by 2, and we'll get x by itself. So x could be pi over 12, or 5 pi over 12, or 7 pi over 12, or 11 pi over 12. And since we are writing all of the solutions, we just have to make sure we list all of those repeating infinitely every pi radians. And that's where you have to be careful, because the period changed. We need to change the period in our solution too. So the next one is 5 pi over 12 plus pi n, and 7 pi over 12 plus pi n, and 11 pi over 12 plus pi n. Now, that's a final answer.